Hi everybody, this is Miss Peachy from your WCA Physical Science class, and I was just recording this video series here because I know we haven't had any virtual class the last couple of weeks due to weather issues. I was at a field trip, and then I will be gone again coming up this coming Monday for a personal day. And then actually next week I also have another field trip scheduled, so it's kind of been a bit crazy, and I want to make sure that you guys have some of the content at least and some alternates to that virtual classes available to you. So this unit we're dealing with right now in physical science, deals with study of motion essentially. So we're going to be looking here today at speed and acceleration and Newton's first and second laws of motion, because they go along with understanding speed and acceleration. Some of this stuff is going to be review for you, and some of this might be a little bit new or an extension of what you already knew. Okay? So looking at speed, remember that speed is going to be a measure of distance divided by time. So speed is how far you go and how quickly you can get there, right? We measure distance in science using the SI system, the System International, which uses the metric system of measurement. Meter for the standard unit of measure, which is roughly 39 inches. And, subunits of that are like 1/1000th of a meter would be a millimeter. 1/100th of a meter is a centimeter. This is showing you a flea, a big blown up version of a flea, but then a millimeter is roughly the size of a flea. And at 50 meters is the length of an Olympics swimming pool. So kind of giving you some scale there. Speed is how far you can get and how quickly you can get there. So distance divided by time is speed. Excuse me. Velocity takes direction into consideration. So not only how far I can go and how fast I can get there, but in what direction did I travel. So that's a little bit different than just speed. Speed is what we call a scalar quantity. Scalar means it's just the amount. And velocity is considered a vector. And a vector includes both the amount and the direction. And that's pretty important when you look at real life situations. Say, for example, you had, if you ever play golf, let's say you're going to tee off, and you're going to, you have your golf tee box right here, right? And then you have your golf ball, and you're going to tee off, and you want to get to the green and get it, in the hole, which is way over in this direction, right? And this is ultimately where you want to end up. Here's your flag. Okay. Now let's say you have a wind, and the wind is traveling, it's a pretty fast wind at 20 miles per hour. Now if you're golfing, it really makes a difference as to what direction that wind is traveling. The speed of the wind is 20 miles per hour. But if the wind is traveling at 20 miles per hour to your back, from your back, I should say, forwards, then maybe you want to use a different club to tee off. Maybe instead of the driver, you're going to use your 6-iron or something like that. Maybe you don't have, maybe it's only a par 3, the hole, and you need to use a lesser club. Maybe instead of the wind traveling in that direction, whoops, I have to redraw the whole thing. Still learning to use this whole function here, people. So, that's okay. I don't mind playing with the drawing tools a little bit. So maybe the wind isn't coming from your back. Maybe instead the wind is actually coming, from your left. In which case you might want to hit into the wind a little bit, because you know that the wind is going to take the ball and move it back the other way. So the direction the wind is coming from is equally as important as how fast that wind is going in this situation. That's why vector quantities are very, very important in real life, because we're not just concerned with how much, we're also concerned with, the direction that it's coming from. Now, for those of you who think math, you're a little bit struggling a bit with the math, I want to introduce something called the magic triangle to you. The magic triangle helps you kind of eliminate the math that's involved in some of these equations. And this works only for like a 3-variable equation. So we have distance and speed and time, and those are our 3 variables. As we saw here, speed or velocity is equal to distance divided by time. So here we can see we have distance on the top. This line means divided by time equals speed. Okay? We can also solve for any variable here. We can say speed times time equals distance, because they're right next to each other. If they're right next to each other, they're multiplied. If they're on top of each other, it's dividing. Distance divided by speed equals time, right? And distance divided by time equals speed. So we can use this triangle to solve for any variable that we want to in this equation. So you don't really have to isolate and figure out how to solve for every variable. It's kind of a nice shortcut when doing a little bit of this math work. Now you see many different units of measure for speed: miles per hour, kilometers per hour, centimeters per second, meters per second. It just depends on what's the most useful in that particular situation, right? We're going to stick with the metric system here. I'm going to actually go ahead a little bit. Remember that velocity includes both the speed and the direction, and we've already kind of talked about that a little bit here. Now the next thing we're going to look at is something called acceleration. And acceleration is change in velocity. If something is getting faster or slowing down or even changing its direction, it's considered to be accelerating. An increase in speed, a decrease in speed, or a change in the direction of motion is considered to be acceleration. Now some examples are, if a car sees a green light and speeds up, that's acceleration. If a car sees a red light and slows down, that's considered negative acceleration. It's also acceleration. Or if a car goes around a corner, it's considered a change in direction, which is also an acceleration. It may not change its speed. It may be traveling at a constant speed, but because it's changing its direction, it is considered acceleration. Now, what these things have in common is that in all those 3 situations, you need to have a force that causes that change in velocity, okay? If I speed up, let me grab my, okay, so if I am speeding up, I have to increase my force, give it a bigger push, right? If I'm slowing down, I have to have an opposing force, like your brakes. And if I'm changing direction, I have to have some sort of force that allows me to change direction. Friction is often the force here. I change my steering wheel, and it's the friction between your wheel and the road that enables you to change direction. If it's really icy and there's no friction, guess what? You don't turn. You go straight and you run off the road. And that's why it's important to have, that friction. You put salt on the road, they put sand on the road, or you slow down when the roads are icy so that you can make sure you have that friction. But all of these are forces. So in order to have acceleration, you need to have a force. And that force is directly dependent upon how big the object is. If I have a small object, it takes a small force to allow them to speed up, just a little push. If it's a big object, you have to push it harder, right? So the force is going to be directly proportional to how big or how massive that object actually is. Well, Isaac Newton recognized this as well. Isaac Newton said that the force is going to be directly proportional to the mass of the object, and, this is going to be complicated, people, inversely proportional to the acceleration. And what he meant by that was that if I have a big object, I'm going to require a lot of force to push it. And if it's a bigger object, if I push it just a bit, it's only going to give me a little bit of acceleration. So the more massive the object is, the less it's going to move when I push it, right? The smaller the object is, the more it's going to move when I push it. All common sense stuff. But what Newton did was he put this in the form of an equation. He said that force is equal to mass times acceleration. That's Newton's second law. And we didn't even do Newton's first law yet. Sorry, struggling with my pen here a little bit. In other words, if I have a very big force, I'm going to make a big F, and I leave my mass, oh, I accidentally zoomed in, guys. This happens sometimes, and I don't know why it happens, but I'm zooming back out here. If I leave my mass the same, then I'm going to have a pretty big acceleration. If I push it hard, it's going to go pretty far. If I don't push it very hard, and again, if my mass stays the same, it's going to have a small acceleration. It's not going to move very far at all, right? That's kind of what this whole law is saying. It's pretty much common sense, but it's stated in a mathematical formula. Newton's first law says, this is how people usually remember it, an object in motion will stay in motion unless its motion is changed by an external force. And I'm going to actually alter that just a little bit. It's only... This thing isn't working super well. Oh, now I zoomed by accident again. I'm going to see if I can write with my mouse, because writing with my pen is kind of being a pain. An object in motion or at rest it's a lot slower, I see, will not change its motion I'm going to actually say pushes or pulls it, because that's what a force is. It's a push or pull. Maybe I should just type next time. So, I mean, it makes sense. An object, say this calculator, isn't going to just move on its own unless it's alive, right? But obviously an object is just going to sit there unless you push it or pull it. And that's Newton's first law. His first law is called the Law of Inertia. So this is called this is what inertia is. I'm going to call this Law 1 here, okay? So an object at rest or in motion, it's only going to move if you push it or you pull it. Again, if a force acts on it is what that means. Force acting on something means you push it or you pull it. And that force depends on how massive it is. If it's a big object, you need a big force to push it. If it's a small object, you need a small force. And how fast the object moves or changes its motion depends on its size too. It also depends on the force, right? So if you hit it with a big force, it's probably going to change its motion quite a bit. It's a very massive object. It's probably not going to change its motion quite as much. So that's what Law 1 and Law 2 explain with Newton's first and second law. They're talking about an object in motion and how that object's motion changes, and how the change in that object's motion depends on how much force you push it with or pull it with, how big the object is. Basically, that's it. And then acceleration, remember, is actually a change in the speed. Either it's speeding up or slowing down, or changing direction. And that only happens if you push it or pull it. Right? That's it. That's the first part of Unit 1 in a summary. I'll talk about the Law 3 and momentum in my next video. So hopefully that helped a bit. And if you have any questions or concerns, feel free to send me a message. Talk to you guys later. Bye-bye.